Crazy voices. Okay, so you know that if you have a nice little circuit with a battery and a light bulb, the light bulb's going to glow, right? Energy is being dissipated. Does that make sense? Are the words that are coming out of my mouth making sense to you? Yes. Energy is being dissipated, being lost, being given off to the environment. So energy is not conserved if you just look in the circuit, right? You have to like include the outside world as part of it in order to talk about energy being conserved. That energy is being dissipated over a certain amount of time. Does that make sense? We've talked about energy per time before. What is energy per time? We've talked about it. Oh man, it was like maybe in October. It was like a long time ago. What is energy per time? Or maybe we wrote it as work per time. What is that? Power. Yeah. Sometimes we talk about power being dissipated or power, like how much power is required to light this light bulb for a certain amount of time. So here's the fun thing about power is that we're going to use stuff that we know already. That definition that we had for voltage. Do you remember what the definition for voltage was that we came up with? We said that it was equal to some stuff. Something divided by something else. Pretty sure we wrote it down maybe last time that we were together taking notes. What did we say voltage was?
Current times resistance.
Yes, we said that. But we also, that wasn't the definition of it. That was just Ohm's law. That's a nice like relationship. What else was voltage equal to? What's that?
Power divided by current?
No, we haven't said that.
Potential energy divided by.
We have said this. Yeah, potential energy per charge. That's what voltage is, right? It's the amount of energy that we have per charge. So joules per coulomb. Goodness, this is annoying. V times Q would then equal PE. Is that okay? So I'm just multiplying by Q on both sides. Then I'm saying, oh wait, here's kind of energy. Electric energy, right? That electrical energy is being converted to heat and light. Okay? So I'm going to say, goodness, that power is equal to V times Q divided by time. Is that okay with everybody? So I'm just putting this definition of E that we had in here, right here. And then somebody out there say, but wait, Ms. Carveling, but wait. I know what this is. What's charge per time? We defined that a couple days ago too. That's current. So really, we can say that the power that's dissipated or the power that's given off, the energy per time that's given off by a light bulb or a resistor or a toaster or whatever it is, okay, is equal to V times I. Okay? Not to be confused with Ohm's law. This is not Ohm's law. It has two things in common. It has a V in it and it has an I in it. That's true. But this is a different equation. Okay? Ohm's law, remember, was V equals IR, right? Those are different things. They're even multiplying, like the I is being multiplied by something different here. Okay? But if you want to know the power that's being dissipated, you can use this one. This one is on your equation sheet. So I wanted to make sure you knew where it came from.
So
Okay?
this is the power that's dissipated, not like the power of the. It's like this is the power of the light bulb, not of the whole circuit.
Well, it depends. It depends on what you're talking about. So if you're just talking about a nice little circuit like this, then it's the voltage across here, which is the same as the voltage here, because we're saying that that wire has very, very little resistance, right? So it means that all of the energy's got to be lost here, and the current is going to be the same throughout the story. So it's the same.
Okay.
So you could say the power dissipated by the light bulb or by the circuit. In just a minute, we're going to do some other things. And when you do those things, then you'll see that the power won't always be the same for the whole circuit as it is for each piece. Does that make sense?
Yeah.
Just to point out, because it may come up, and I just want to make sure that you've seen it. sometimes we like to write this equation in different ways, like by taking this V and plugging it in here. If we do that, then we've got P is equal to I times R times I, or we'll write that as P equals I squared R. It's the same equation, we're just plugging things in. You don't have to memorize that. I don't even think it's on your equation sheet. I just want you to see that it also exists, and you can use it, okay? You can also write Ohm's law the better way, the way that actually makes sense because you've got cause and effect, right? V over R is equal to I. And if you do that and plug that into the definition equation, then we can say that P is equal to V times V over R. So P is equal to V squared over R. So these three equations are all equivalent. They're just nice to be aware of, depending on what information you're given. Does that make sense? So if you're given resistance and given current, then using that middle one's going to be a whole lot easier than having to find the voltage first. But you could go back and find the voltage first and then just use the top one, and that's okay too. Is that okay with everybody? I'm not going to give you the examples here, but let me just throw this out at you. If you were given power and you were given current, could you find the voltage?
Yes.
Yes, right? If you were given voltage and you were given resistance, could you find the power? Right? Like, this is really not hard stuff. I just want to make that really clear. If you were asked to do a ranking task and they gave you the current and they gave you the power, could you rank by resistances? Yes, right? Okay. Issues or questions with that? Is that all right? Okay. So we are going